So the final example that we're going to work through, number 6. The velocity of a particle p at time t seconds, so v equals 3t squared minus 8, 5. When t equals 0, the position vector of p, so it's giving me an initial condition, so chances are I'm going to integrate, and we want to find the position vector of p after t seconds. So the position vector we get by integrating the velocity vector, which means we're going to be integrating 3t squared minus 8 and 5 with respect to time. That works out to be 3 over 3, so that's t cubed minus 8t 5t. We've integrated, so we need to consider the constant of acceleration. The initial conditions we're given are when t equals 0, its position is 2 minus 4. Those are all in terms of t, so therefore AB equals 2 minus 4, and the position, and it's the position of p, and we're going to come to a q now, so let's put the little suffix in there, rp, so rp will be t cubed minus 8t plus 2 and 5t minus 4. So the position vector of p after t seconds is given by that. Then we come to part B. So second particle q moves with a constant velocity of that. So vq is 8, 4. When t equals 0, we have another position vector given to us, so we can work out the position, the function for the position vector of q. Prove that p and q collide. So in order for p and q to collide, both of those particles need to be not only in the same place, but also at the same time. So what we're going to be doing is, first of all, getting an expression for the position vector of q. So the position vector of q will be given by that. So 8t, 4t plus a constant. We know that when t equals 0, we have an initial condition for that. So when t equals 0, rq equals 2i, 0. Both of those are in terms of t, so AB will be 0. So therefore RQ equals 8t plus 2 and 4t. Now, for that collision to occur, RP must equal RQ at the same instant of time. If the time values are different, it just means they're either following each other or their paths have crossed. But for it to actually collide, that particular point has to occur at the same value of t. So if we look at our two expressions, what we're saying is that t cubed minus 8t plus 2, 5t minus 4 must be the same position as 8t plus 2 for t. So both of those equations only have t in, so if we compared the j components or the I components, they're just in terms of t, so we can calculate t. So what we do is we take one row, say the j in this case would be the easier one, to solve for t, and then whatever that value of t is, we substitute it into the other component, so in our case the I component, and make sure that that value of t holds true for the left hand side and the right hand side. If that's the case, then a collision will occur. So from j we get 5t minus 4 equals 4t. So from that, t equals 4. So a value at the time t equals 4, the j components are the same. So we now want to check that that holds true for the I components. So if we put that into the i's, just move this up a little bit, we have 4 cubed minus 8, 4 plus 2 equals 8, 4 plus 2. So 4 cubed is 64, minus 32 plus 2 equals 32 plus 2. 64 minus 32 is 32 plus 2 is 34 equals 34. So that's consistent, and therefore at t equals 4, Rp and Rq have the same position vectors and collision will occur. So this is testing your understanding about how vectors work and how the time relates to those vectors. Okay.